Okay, so it's the last talk of this morning's session will be given by Sthitadhi on measurement invisible quantum correlation in scrambling dynamics. Please.
Thank you. Let me start by thanking the organizers for putting together this meeting and inviting me to speak here. It's always great to be in ICTS. Okay, so I'll talk about measurement invisible quantum correlations in scrambling dynamics. But before I start the talk, let me just put two disclaimers. So the first is that this is a very sort of different audience to the kind of audience I'm used to speaking to. So if there is some confusion regarding the language, terminology, etc., do please stop me then and there, and I'll try to clarify. The other thing is, for the same reason, if you notice some oversight in terms of referring to people or things that are probably known from before, again, just let me know. Okay, so this is work that was done with a PhD student here who's working with me and Abhishek, Alan Sherry. He's over there in the audience, and this is the reference to the work. I'll be happy to take questions in the middle of the talk, but in all the cases, I'll just refer you to Alan because he's the one who did the work and I'm the one who's giving the talk. Okay, so I know this is the last talk before lunch, so if you are hungry, please free to leave at any point. And because of that, let me start with a summary of the talk so that you have some takeaway message. So this is the setting that we will consider. There is Alice, there is Bob, they have a state which may or may not be entangled. And what Alice does is she does projective measurements on her part of the system and conveys these results to Alice classically, okay? And conveys these results to Bob, sorry. And what Bob can do is he can do a full tomography on his state. And he can ask the question that the state that he sees on his part, is that sensitive or not to the measurement outcome that Alice had communicated to him classically, okay? So now here's a trivial situation where, for example, there is no entanglement between the two states. They are literally sort of separable direct product states. So in that case, it's not a big surprise that the state that Bob sees is completely agnostic to whatever Alice told him about his measurement outcomes. And the other sort of extreme limit, which is again not that unexpected, is the state is very strongly entangled, and whatever Bob sees actually does depend on the measurement outcomes that Alice had conveyed to Bob classically. Okay, so these are the two sort of situations which would not raise any eyebrows. But what we actually found was a phase, or I'll say why is it a phase, but we found a phase or a situation, let's say at this stage, where the state is entangled, and yet Bob's state is agnostic to Alice's measurement outcomes, okay? And that's sort of the key result of that entire work. We call this measurement invisible quantum correlations, for want of a better word. And given my background in sort of general quantum dynamics and many-body theory, we were quite excited that we could show in certain limits analytically and in general numerically that there exists a phase transition between these three kinds of situations, and it arises very naturally, without much sort of looking for. It arises very naturally in chaotic or scrambling quantum dynamics. Okay, so that's sort of the lightning summary of the entire talk. So now to get further into the talk, I hope what I managed to convince you is that the key idea in this entire work is the entanglement structure in a state and how that entanglement structure actually responds to measurements on a part of the system. Okay, so that's sort of the key idea. Now, the reason this is slightly, or the reason we have to be slightly careful about this is that there are different facets of saying, different facets of an entanglement structure. So in sort of condensed matter theory or quantum many-body theory or quantum stat mech, where I come from, entanglement actually has emerged as a new paradigm for classifying phases or states of quantum matter. And again, this is in the many-body setting. And roughly speaking, you can classify the questions here into three categories about entanglement. The first is how much entanglement. The second is range of entanglement, and the third is how multipartite is the entanglement. And one needs to be slightly careful about sort of distinguishing these three facets of entanglement. So again, just to put some words to it, if we say that a state is area law entangled, we say that, oh, that actually means that it has a very small amount of entanglement in the thermodynamic limit. On the other hand, if it is volume law entanglement, then it has an extensive amount of entanglement. Similarly, if I say something is short-ranged entangled, it means that only the degrees of freedom nearby are entangled with each other. Whereas if I say something is long-ranged entangled, then it means that degrees of freedom in an extended system, which are really far away from each other, can also be entangled. And then finally, we have the notion of how multipartite is the entanglement. So if I say a state is few-partite entanglement, that means that I can have an extensive system, but that extensive system can actually be broken up into clusters of few partite entangled clusters. And these clusters can be, again, sort of non-locally distributed in space, such that you might end up with a large amount of entanglement, but it continues to be a few partite entangled state. And then, of course, you have the other end of the spectrum, which is a multipartite entanglement, where the entanglement is genuinely shared across a large number of systems, a large number of degrees of freedom, and you actually cannot do this decomposition even approximately. So these are just words, and these are probably best illustrated with an example. Okay? So here's an area law entangled state. Imagine I have qubits on a chain, and these red lines actually show, say, bell pairs or some singlets that these qubits form. And notice that all the singlets are very, very short ranged. Only a qubit forms a singlet with another qubit which is really, really close to it. So this is a classic example of a short-ranged area law entangled state. And these kinds of states appear quite naturally in sort of ground states of gapped local Hamiltonians in 1D. That's a theorem by Hastings. And more recently, we also know about many-body localized eigenstates in strongly disordered systems, where such states actually appear throughout the energy spectrum of the system. Okay? Now, the other case is you can have, again, area law entangled states, which are not necessarily short-ranged, but they have long-ranged entanglement. So this is important because here, the fact that the entanglement is long-ranged does not immediately mean that there's a lot of entanglement. So there is a very small amount of entanglement still, but that entanglement is present at all length scales. Okay? So again, a classic example is topologically ordered states. For example, the ground state of the Kitaev toric code. Okay? Now, these are sort of the rough classification for area law entangled states. I can do a similar game for volume law entangled states. So of course, if I have volume law, then this is what is often called a rainbow state. It's a cooked up state, but sort of illustrates my point well, so I've put it there. So you see what I've done here is, again, I have qubits on a line, and it forms singlets or bell pairs, which are extremely long-ranged. See, almost all or a macroscopic fraction of these bell pairs live on scales which are extensively large. However, this is this volume law entanglements, if I put a cut here, I'll get an extensive number of bell pairs that need to be broken, and that gives me a volume law entanglement for a state like this. But notice that this volume law is actually made up of a collection of many, many bipartite objects. These bipartite bipartite entangled objects happen to be separated by large distances, and sort of that gives me the volume law, but the entanglement is not genuinely multipartite in this case. And if you want a genuine multipartite volume law entangled state, then again, sort of the simplest, least structured example is a Haar random state. These also are states which are very close to Haar random states in a certain sense of the word, do appear naturally as eigenstates or time-evolved states of quantum chaotic systems or scrambling systems. And here what happens is every qubit is entangled with an extensive number of qubits. There is volume law entanglement, but given entanglement monogamy, and given that a particular qubit shares entanglement with everything else, any bipartite measure is extremely small, in fact, vanishingly small in the thermodynamic limit. Okay? For example, if you ask what is the entanglement between this qubit and this qubit, in the thermodynamic limit, it will go to 0. I mean, measures such as mutual information, concurrence, these would go to 0. And this is a sort of signature of the fact that the entanglement is not sort of few partite, it's really multipartite. Now, the thing is, in this zoo, it seems if you have scrambling dynamics, then no matter where you start from, you always seem to end up with a situation where you go to a multipartite volume law entangled state. And that's sort of the feature of any scrambling unitary dynamics. That scrambling unitary dynamics can be sort of affected by a random unitary circuit, a Floquet random unitary circuit, a chaotic Hamiltonian, doesn't matter at this stage. Eventually, at long enough times, you will end up with a state which is morally like this. So there is this transmutation of quantum entanglement. And the specific setting that I will be sort of concerned with is the following. Let's say I have two groups of qubits here. And initially, every qubit here forms a bell pair or a singlet with some, with one randomly chosen qubit from the left half. Okay? So this is obviously an example of this kind of a state, okay? Which is volume law, but not multipartite. Then I run a unitary circuit on this part of my system. I don't do anything to this. I run a unitary circuit on this part of the system. And what obviously happens is that it forms a very, or the initial entanglement, which was literally a collection of bipartite entanglements, transmutes into a multipartite entanglement. Now, of course, how multipartite is this depends on how scrambling this unitary is. And that is controlled by the nature of the unitary, how deep the unitary is, and so on and so forth. So what we then do is we perform measurements, and this is Alice performing measurements on a part of her state, and we ask what is the state on this sort of reference given the measurement outcomes. So that sort of sets up the question, which is what is the manifestation of the entanglement structure if I do local measurements on a part of the system and I ask for the reduced state on another part conditioned on the outcomes. Okay? So that sort of precisely puts forward the question that given a particular entanglement structure, what can we say about this from a protocol like that? Okay? All right, so let me take a slightly more baroque and detailed version of the model that we used. So it's not very different from what I had in a cartoon sense on the previous slide, but this is just to set up the notations and the definitions. So I have n qubits here, call this subsystem Q. I have gamma n qubits here. Gamma is a number which is less than 1, but note that both these numbers are proportional to n. So everything in this case is going to be extensive, and eventually at the end of the calculation, we would like to take n going to infinity to define a phase, because we know phases are defined in the thermodynamic limit. Okay, so, and these are the bell pairs. It forms gamma n bell pairs, and then I run this unitary circuit for a depth which is again tau times n, because I have a system of n qubits. So I run the unitary circuit for a depth which is also proportional to n. And finally, I trace out a part of Q which I call E, and the size of E is 1 minus p times n. P is a fraction between 0 and p is a number between 0 and 1. And on the remaining Pn qubits, I actually do measurements. Now, there are two things that I need to define here. The first is, before I do the measurements, but I trace out this E, I am left with a mixed state of RNS, which I'll call rho RS. And then I do projective measurements on every qubit in S, and I get a conditional state on R, which I'll define, or which I'll denote as rho R of OS. Okay? And of course, there's a probability of getting a particular measurement outcome, and P of OS is the probability, rho R of OS is the conditional state. These things put together over all possible values or all possible measurement outcomes define an ensemble of states for me in R, and that ensemble is over the measurements or measurement outcomes in S. Okay, so, and of course, if I just trace over S as well, I get the reduced density matrix of R, which is nothing but the probability over all the outcomes times the conditional state on R. Now, two things need to be noticed here. One is that because the unitary only acts on this part of the system, the entanglement between R and S union E remains gamma n log 2 at all times. Now, this is a simplification because it just tells me that I only need to worry about the transmutation of entanglement from bipartite to multipartite. I don't actually need to worry about the generation of entanglement. Yes?
I have a question about the measurements on S. Are they tomographic? That's to say, do you vary what basis you measure, or you use a certain basis?
So we only measure the computational basis.
Because that's, of course, a bit restricted.
Sure. But the thing is, we think it doesn't really matter because we average over these unitaries eventually. So because I can, if you want me to measure, say, a different, say, instead of measuring sigma z, you want me to measure sigma x, then I can always put single site Haar random gates here, and I can absorb them into this Haar random unitary over here. So, and all results I'll show eventually will be averaged over ensembles of these unitaries. Thank you. Okay, so as I said, the entanglement essentially is gamma n log 2 at all times. And in fact, given that I chose this bell pair state as my initial state, rho r is identity at all times. Okay, but this is just a simplification. Our results actually do not depend on this being gamma n log 2 or rho r being identity. All I want is some extensive amount of entanglement between r and q at the initial time. Okay, so two questions. First is, are R and S entangled with each other? Because if R and S are not entangled with each other, then it's almost meaningless to ask the question about measurement visibility, although it's not completely meaningless. I'll come to that in a minute. And then in order to understand the measurement visibility, you ask the question that, is this ensemble of states on R non-trivial? Okay. In particular, you'll notice that there are three parameters in my model. One is the depth, tau, the number of qubits I trace out, or equivalently the number of qubits I measure, controlled by p. And of course, I have gamma, but gamma I'll sort of keep fixed because it's difficult to scan a three-dimensional phase diagram. So we'll take gamma to be 0.2, doesn't really matter. It just changes things quantitatively. And we'd like to know what happens to the answers to these two questions in the limit of n going to infinity. So, yeah.
I mean, you talk about limit, and now R and S are mixed, right?
Sure.
So they can also be classically correlated.
They can be, and I'll come to that in a minute. Absolutely. Okay, so, and that sort of gives us a phase diagram in terms of the entanglement structure, specifically the entanglement structure's response to measurements. Okay, all right. So that sets, this is the setup. These are the two questions we are interested in. How do we quantify these things? So this state of R and S is a mixed state. So I cannot use von Neumann or any entropies. What we choose to use is the logarithmic negativity. This is defined in this way, where rho Rs is the density matrix of R and S. You take a partial transpose with respect to S, and then you take the trace norm, you put a log. This is known to be, or this has been shown to be an entanglement monotone. I'm not going to get into the details. This is a measure of sort of the entanglement between R and S. So what is known is, if rho Rs is separable, then the negativity or log negativity is 0. The contrapositive of this is, if my log negativity is non-zero, then R and S are necessarily entangled. Now, separability for mixed states actually means that I can write it in this way. Okay, so for separability for pure states means that I should be able to write it as a direct product. Here it means that I should be able to write it in this form, which I think Bauer meant as a classically correlated state. Now, there is one sort of catch here, and this is a caveat I should mention, which is, if NRS is 0, it does not necessarily imply separability. Okay, a counterexample is bound entanglement. But as far as we can tell from our results here, this situation does not arise in our case. So for the rest of this talk, for our purposes, we'll take NRS equal to 0 as a working criterion for being disentangled. Okay, so that's the measure for entanglement. We need to ask questions about measurement visibility as well, because there are two questions I had posed. So remember that given a measurement outcome OS here, I have an ensemble of, or given a measurement outcome OS, I have a state rho R of OS. that is the state of R conditioned on that measurement outcome. And very naively, if rho R of OS is completely agnostic to OS, then we should just have rho R of OS to be the reduced density matrix on R. On the other hand, if rho R of OS does indeed depend on the measurement outcome, then the ensemble of states is going to be non-trivial. So how do I quantify that? I just quantify that using the spread of that state over all the possible measurement outcomes. So this quantity is the trace norm of rho R of OS with respect to rho R, and that's then just averaged over all the measurement outcomes. Okay? So if delta RS is equal to 0, that necessarily implies that rho R of OS is just equal to rho R, and that again is my definition of measurement invisibility. And delta RS being finite is my definition for measurement visibility. So we now have two quantifiable or computable measures for the two properties that I wanted to ask about the entanglement structure. Okay, so what are the different possibilities? So the first possibility is you have entanglement and you also have measurement visibility. That's not unexpected. That's sort of, if you remember, that's sort of the cartoon I had on the extreme right in the beginning of my talk. The other possibility is that NRS is equal to 0, which means it's disentangled, as I said, for all practical purposes, and it's also measurement invisible. So it just means that the state is very, very close to a product state. The third possibility is NRS is equal to 0. It means that the state is not entangled in that sense, and yet delta RS may not be 0. And this does happen for classically correlated states of this kind. Probably this is the sort of situation you were worried about. Now, as I said, as far as we can tell, this does not happen. This situation does not sort of present itself in our setting. And then the most interesting part for us is you have entanglement. Along with that, you have measurement invisibility. Okay, good. So now let's ask, where do these different possibilities show up in our phase diagram? Remember that I had parameters tau and p as my phase diagram. Tau is the depth, p is the number of qubits I actually measure, 1 minus p, or pn is the fraction of qubits I measure, 1 minus p is the fraction of qubits I trace out. So let's first ask, what happens at tau equal to 0 when I have not applied any unitary? In that case, obviously, there's a finite fraction of measured sites which necessarily form Bell pairs with the qubits in R. So that naturally means that the state of R is sensitive to the measurement outcome, because if I have a Bell pair, if my measurement outcome gives me up, I know that the state in R is down, and if my measurement outcome gives me down, then I know that the state on the Bell pair, on the state of the qubit in R is up. So there is a clear distinction in rho R depending on the measurement outcome. And R and S are entangled by construction. So this entire line at tau equal to 0 is necessarily entangled and measurement visible. Let's go to the other extreme limit where I have tau equal to infinity. Now tau equal to infinity is a limit where I can approximate this unitary circuit as a gigantic Haar random unitary acting on a 2 to the power n dimensional Hilbert space. And that actually allows complete analytic calculations. And in that case, we can actually show that there are two transitions in this model. The two transitions happen at critical values of p of 1 minus gamma and 1 minus gamma over 2. And this is an entanglement transition. You see, it goes from being disentangled to entangled. And this is a measurement visibility transition. It goes from being measurement invisible to measurement visible. So we do have the three possibilities. Again, this yellow and the purple phase are probably expected. This is a completely new phase that we had not expected and therefore is of interest. So, and then we can do numerics for some local Haar random circuit. And this is what the phase diagram looks at. For finite values of tau, you see that. So these 2 points are analytic results. These are all numerical results. And of course, in this limit, the numerics is extremely messy, so I'm not going to comment too much. In fact, the fourth phase that I had sort of said that does not appear in our setting, even if it is there, it's probably somewhere there. These over here, the numerics are sufficiently kosher. In fact, these are cuts through this phase diagram. We use the classic diagnostics, classic signature of data points crossing as a function of system size to detect where the transitions are. So this is the negativity as a function of p. So these two plots are a cut along this line. These stars mark the critical points, whereas this cut, this purple line, is these two plots where things have been plotted as a function of tau, and again you have two critical points. All right, so that establishes the phase diagram. What can we actually say? This entanglement transition is nothing but a decoupling transition. And decoupling transitions we know from textbooks and also in the context of measurement-induced entanglement phase transitions and so on and so forth. So the basic point is over here, you see p is quite small, which means 1 minus p is large. What that means is I have traced out a sufficiently large number of qubits such that the multipartite entanglement that was there between R and S union E has sufficiently been annihilated. In the sense that once I have traced out a large number or sufficiently large number of qubits, I have removed all the qubits which were mediating the entanglement between R and S. So that's why I do not have any entanglement in this phase. This is a measurement invisibility transition. Here, the number of qubits I trace out are not large enough to kill the entanglement between R and S. In fact, it's not large in this entire region. However, the entanglement was multipartite enough that once I do one local measurements on S, the state of R is not agnostic to that. Okay, so that's basically this transition. And this is really the crux of the story, that we do have these three phases which are very distinct in terms of their entanglement structure, not necessarily in terms of just the entanglement. These are very different in terms of a slightly finer measure, which is what is the structure of the entanglement and its response to measurements on a part of the system. Okay, so that's actually the main sort of result. Let me say a few things about implications. So the first implication is this sort of allows us to, with some trepidation, it allows us to make a slightly stronger statement about quantum steering. So what is quantum steering? I guess I don't need to explain steering to this audience, but nevertheless, just to put us all on the same page, imagine I have, again, Alice and Bob. It's the same setup as before. Now the point is, conventionally it's formulated as Bob does not necessarily trust Alice's measurement apparatus. So the point is that Alice conveys her measurement outcomes to Bob. Bob does tomography on his state. And the job of Alice is to convince Bob that their states are necessarily quantum entangled. And Alice actually was not using any prior information about Bob's partial states. That's this local hidden state formalism of this problem. Now, there are results which actually show that all bipartite entangled pure states are necessarily steerable, which means that if I have a pure state between Alice and Bob, which is entangled, then Alice will always succeed in convincing Bob that the state is genuinely quantum entangled. However, in our case, we have the measurement invisible quantum correlated phase. In that case, what happens is that the state of Bob is independent of Alice's measurement outcome. So the state appears completely uncorrelated to Bob because whatever Alice tells him, as far as the measurement outcomes go, Bob says, no, I still get the same state all the time. So in fact, Alice not only fails to convince Bob about entanglement, she also fails to convince Bob about quantum correlations. So this is a slightly stronger statement about steering, and that's actually possible because the state is mixed. So that helps us get around these results, and we end up with a situation where we have entangled and yet unsteerable states. There's another implication, which is the factorization of probabilities of bit string probabilities. So given a state, you can ask that there's a particular bit string that you measure. What is the probability that you get that particular bit string? So let's say Alice measures observable OA with some outcome OA. Bob measures observable OB with some outcome OB. And there's a joint distribution of these two outcomes, which is nothing but this, where rho is the state between A and B, and these two operators are projectors onto the eigenstates OA and OB. So now I can ask, what is the conditional probability that A gets, or Alice gets OA, given Bob gets OB? That's just this. And again, in the measurement invisible quantum correlated phase, rho A of OB is independent of OB, so I can just replace it with OA. That just gives me P of OA. So that means that this joint distribution does actually factorize into P of OA times P of OB. So I think there are some other implications of this. There are some experimental prospects, which I think I'll skip over. And I'll quickly summarize. So this was the original situation, sort of summary. The summary slide is not pretty much the same as the first summary slide. We have the disentangled measurement, sorry, this should be measurement invisible, this is a typo. It should be measurement invisible phase. We have the entangled and yet measurement invisible phase. We have the entangled and measurement visible phase. This is the phase diagram, and this is where you can find all the details. But let me say a couple of words about what we are sort of working on in this direction in the sort of immediate future. So these are works in progress with Alan, another PhD student here, Saptarshi, and Peter Claes, who is at Max Planck Dresden. And so a natural sort of extension of this question is what happens to that phase diagram when you have bulk measurements? Because we know that bulk measurements in a circuit can drive a measurement-induced entanglement phase transition. But this is, there is a certain motivation to this question. It's not that we have a setup, so why don't we apply it to a circuit with measurements? There's a precise physical question we are asking here, which is that is the root of the stability of the volume law phase, which is also the root of the measurement-induced phase transition, actually due to decoupling, or is it due to the measurement invisibility phase transition? So, in other words, there could be two situations: that the volume law phase is stable because a large enough subsystem, or if a large enough subsystem is traced out, then the two parts of the system are purely decoupled. That would have been this phase over here. Or the other possibility is that there is still some residual multipartite entanglement near the measurement-induced phase transition, but it's not visible to local measurements. Okay, so that's one of the questions here. The other question that we are also working on quite actively at the moment is the following: that imagine I have a situation where there is spatial structure to the circuit. I have some locally brickwork-like circuit, or it could be time evolution with respect to a local Hamiltonian. So such circuits have a light cone structure to the quantum information there. So now the point is, can this measurement visibility transition be used as a signature of the space-time profile of information spreading? In fact, can it have analogous information to out-of-time ordered correlators, but in an operator independent fashion? So these are two things which we hope we will have something to report on very quickly with these three people. And yeah, I think I'll stop there and just leave the summary slide. Yeah, thank you.
Okay, thank you. We have time for question. Yeah.
A couple of sort of related things. In this left-hand part, this disentangled phase, you implied from what you discussed that you believe that the state, in that case, the rho RS, is close to a product state. That seems like a somewhat non-trivial assertion. Did you have any means of checking that? Say,
yeah, so
additivity of entropy or something like that?
So we sort of checked that the negativity does go to 0. That, of course, does not mean that it's. We also checked the following. So we had rho RS minus rho R cross rho S.
Yeah.
And this also seemed to go to 0.
So that's
at least it went down.
Small.
Yeah, it's really, really small.
Okay.
In fact, but I'll just make one more comment. So in this particular limit, it's not very unexpected, because there are results analytically proving that in the thermodynamic limit, that if you take a Dhar random state, so if I take a Dhar random state, and let's say I make a tripartition, so let's say A, B, and C, and I trace this part out. If this C is more than half of the system, then the states of A and B do indeed separate. So that's a paper by Ashwin and company.
And then another small thought or clarification. You've, in that phase diagram, you've scaled out N completely. And
yes.
Do you believe this is indeed a stable phenomenon, that it's seen for large N? And what would be the situation with finite size corrections?
We don't know.
Okay.
So instead of saying things which may or may not be correct, let me just show you the data that we got. So it seemed like if I plot things as at a fixed tau, for example, we see as clear signatures of crossing as you see with 16, 18, 20 qubits. But that's what I'm going to base my statements on.
Okay, we have a question.
Yeah, so let's say for this other case that you didn't get, that is classically correlated, but measurement, like there is no entanglement, but still measurement visible, right? So can you think of doing something like, let's say, this unitary organized such a way that it gives some kind of critical point where the classical, like large correlation link, maybe with some MBL Hamiltonian which has some critical points, right? So then you can increase probably mutual informations and all, like the classical correlations, because your correlation link diverges. Maybe you can get such phase, right?
I see. What we were, or at least what I naively thought was, if I introduce some dephasing within this circuit, that also might give me some classical correlation. But at least, so, okay, I should say something here that, if this line happens to cross this line somewhere, we will actually end up with that phase. Now, whether this is already there in this very messy part of the phase diagram, I don't know. But your idea might work and show it cleanly.
Hi, hi, Sthitadhi.
Yeah.
Hi. So just a quick question. So I'm actually really perplexed as to what kind of entanglement structure that there is. I have a couple of questions. The first one is, could you give us some sort of intuition, maybe an example of what kind of entanglement structure could exist in this many-body state, where NRS is non-zero, but then the thing is invisible, which means that every measurement outcome is being driven to the same state? This sounds very mysterious to me.
I mean, that's why we wrote the paper.
What is the analytical structure of the states here?
What do you mean by the analytical structure?
Like, what do they look like if you write them down for like 2, 3, 4 qubits?
This phase, I mean, this whole thing does not exist for 2, 3, 4 qubits. It's a phase, so it's for infinite large size.
Yeah,
I can give you.
It'll have some decaying thing, which then as you go to.
Yeah, so I can give you a wave function numerically.
Okay.
Large, whatever Hilbert space dimension you want, let's say 2 to the power 20, I can give you the wave function. I don't know what it looks like. My hunch is what really happens is, and again, this is a very cartoon, possibly or definitely incorrect way of thinking about it, which is I have these degrees of freedom, and if I really think of the entanglement as some net of correlations which strings, which sort of goes over all of this, then in this phase what happens is that the number of qubits I'm tracing out is sufficiently large that once I do one local measurements on this, the entire network immediately snaps. And therefore, the state that you get on R actually never sees the outcome. That's the best picture I can give you.
And just one more clarifying question. So the analytics is in Dhar, right? So you just did the Dhar. And the numerics is in CL2?
Is in what?
In Clifford 2?
No. This is just a Dhar random, but brickwork circuit.
Brickwork Dhar random.
In fact, we also have a result for a non-integrable Ising model. Looks pretty much the same.
Okay, so it's something that survives kind of higher moments of the.
Yeah, absolutely.
Hello.
Yeah.
Thanks a lot for a nice talk. So in the implication, you mentioned a point regarding the multipartite steering scenario, right? In the implication part, like we can think of this scenario as in terms of steering.
Yeah.
So can we think something in the context of non-locality in multipartite system?
Yeah, so that is the natural way of thinking about it. And I think I can't seem to get beyond drawing these kinds of cartoons, that there is a non-local net of correlations, which whether it snaps or not depends on how many qubits you measure and how non-local it is. But that's as far as I can get. I mean, if you're asking for something quantitative, then I have those two quantities for which I already showed results.
So last question, I guess.
So I have a rather naive question. So there's this interpretation of the volume law of phase as an error correcting code in itself.
Absolutely.
So in that context, now that you have two kinds of phase transition, does it mean that the middle one that you have is like an error correcting? Is that a trivial interpretation? Like can I interpret the middle phase that you have as an error-corrected code in itself? But the lesser measurements or more measurements that you have, the more correlated it is, doesn't necessarily imply that it's a self-correcting code, but in the mid, because it's not agnostic to.
It's a fantastic question, and that's why we are trying to answer here. Because I'm sure you know this paper by Sunwon Choi and Ehud Altman and company, where they show that the measurement-induced phase transition is nothing but the error-correcting phase transition. So we are asking whether that error-correcting / measurement-induced phase transition is due to decoupling or this new phase that we have got. So this, hopefully, this paper will answer that question.
To your question, the paper by Choi, they showed that for this measurement invisible phase, that you can recover the initial state for just local operations on S. So there will be references there. So that paper covers that particular question about how this is an error correcting code for measurement errors.
So I think if you go by Choi's work, then this is the transition that they are talking about. So in principle, they'll probably say that everything below that is volume law and everything above that is area law. So,
okay, so thanks again for this
thank you.
talk.
Thank you.